Hello, this will be the last video from this chapter on wave optics. So this is going to be a relatively short video, and really I just want to so we're going to skip over some of the math here on the left, and really I just want to talk about the complete double slit intensity. So in the previous videos we learned about the effects of interference and diffraction. So interference because of two different slits, or multiple slits, so light coming from multiple slits interfering with each other. And then diffraction is light from a single slit interfering with light from another part of that same slit. So if you actually perform a double slit experiment, there are actually effects of diffraction that we ignored before. So this picture right here actually shows what a real double slit pattern would look like in real life. And actually from this picture we can get a little bit of information. So this question right here asks, if the slit width is 40 micrometers, what is the slit separation? Okay, so in other words, if A equals 40 micrometers, what is D? D equals what? Right, A is the variable that we've been using for slit width, and we're assuming the same slit width for both slits. And D is the center to center slit separation. Okay, so I wanted to just quickly go over what happens in the single slit case. So this is one slit, and then in the double slit case in the ideal. So not ignoring the effects of diffraction. So this one we've seen before. If we're wanting to plot intensity versus position y on the screen, we've seen this one before. This was the cosine squared plot. So remember the intensity gets, it's more and more narrow as the number of slits increases right here. So in that case, they get more narrow and they get higher. But for the two slit case, this is a nice cosine squared function. So it looks something like this. So in other words, intensity as a function of y, is proportional to cosine squared of not quite y, but something related to y, right? It's something related to the path difference, and more so the phase difference, right? Now this one on the left, let's do a different color here. So for the single slit case, your book talks about what happens in the single slit case. So this is the mathy part before. So they use something called phasors, which is really nothing more than just arrows in the complex plane. So it's a fancy sounding word that means all sorts of things if you watch Star Trek, I guess. But here it's nothing so crazy. It's just it's a nice way of dealing with trigonometric functions where they're slightly out of phase. So you can treat light coming from different parts of the slit as different phasors that add together, and really there's not just one. Like if you consider the slit, really there's infinitely many pairs, so you have to have a bunch of phasors that are really small in magnitude. So they build this up, and what they get here, and the main result of what they derive is that the intensity for the single slit case is proportional to sort of a weird looking function. It's sine squared of something they call beta over 2. So again, beta is related to a phase difference. It doesn't really matter what the exact definition is, divided by beta over 2 squared. So sine squared x over x squared. So at big X, this goes like 1 over x squared. So this actually dies off pretty quickly, like 1 over x squared. And then you might remember also from calculus, in the limit that this goes to 0, so limit of sine x as x goes to 0 is x. So this thing will have some maximum right at 0. So this function looks something like this, and the intensity just really drops off. So you have this spot right here, and actually I should draw these equally spaced. So let's see. Here, here, here. So I'm trying to draw these so that this. In the small angle approximation, these are all equally spaced, right? This one's the one corresponding to p equals 1. This is the p equals 1 dark spot, p equals 2, p equals 3. And yeah, in the small angle approximation, they're all equally spaced right here. And then this central maximum that's twice as wide, because there's the missing dark spot, and then kind of looks like this. Okay, so there's a minute, goes down to 0, goes down to 0, goes down to 0. So you can show using this function exactly how much, I mean, you could integrate this from here to here, and then you can also integrate it from -infinity to infinity to see just how much of the energy is in that central bright spot. You'll get most of the energy is actually in that central maximum. So what I want to look at now is actually combining these two. So what happens in real life? So in real life, when you combine both of these two effects, what you get is a combination of these two things. So you actually get what's called a diffraction envelope. Ooh. So in real life, the intensity versus y, it's going to be a function where you kind of have hints that there are diffraction going on. But then in addition to that, you get the cosine squared piece. So go like this, you'll get a bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. And then it'll kind of overall get dark right there. And then overall you'll get bright, 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 maybe a few bright spots there, and then dark, and then maybe some vaguely bright spots on the right hand side. You get the same thing on the other side, right? It's symmetric. Dark right there, bright, bright, bright. So you're getting, so you see what's happening? You have the cosine squared piece of this, but it's mitigated by this envelope function. That's the diffraction. So really the overall intensity, so in real life, the overall intensity is a product of these two pieces. So there's a sine squared of x over x squared piece, and then there's another piece that goes like cosine squared y. So x and y are different phase pieces. They have to do with the slit width and the slit separation. So the x piece here depends on the slit width, and the y piece depends on the slit separation. Okay, so you can see this here in this real life picture. So you see how there's overall this central maximum. That's a little hard to see. So overall you have this central maximum right here. And then you get these, so it looks like this is a diffraction effect. That's the central diffraction maximum. And notice how like here there seems to be a diffraction minimum, here. It looks like they're roughly equally spaced, but then there's a missing one right here, and then there's one here, one here, one here. So we're pretty confident that that's a diffraction effect. That there's the missing. So if you're ever looking at a interference pattern, and you get dark spots, but then the one in the middle seems to be missing. So all of these dark spots are equally spaced except the one in the middle. That's a pretty strong indication that you're looking at diffraction. So that's the diffraction effect. But then we also notice, so you notice how there's a bright fringe right there, and we can't really see a dark spot there because the photo is a little overexposed. But you imagine if there was less light, maybe there's a dark spot right there, and it looks like there's another maximum right here. It does look like these things are coming in pieces right here. So the center right there was actually the m equals 0. So let me label this one right here. This is m equals 0. And I'm just counting 1, 2, 3, 4, 5. Did I count right? 1, 2, 3, 4, 5. Looks like the m equals 6 one is missing. So m equals 6 would be there, but it also lines up with the dark spot. This is the first diffraction dark spot, p equals 1. And that looks like we have m equals 7, 8, 9, 10, 11, and then m equals 12 is missing right there. And this corresponds to the p equals 2 dark spot. So this is m equals, you get 0, 1, 2, 3, 4, 5. You're getting all these numbers right here. You're getting all these bright spots. And so the intensity would be uniform. It would be the same for everything, except there's this overall effect because of the slit width that's providing this diffraction effect. So actually the fact that, so for this picture in particular, it looks like the m equals 6 bright spot is missing. So for this problem right here, this is called a missing bright spot. missing bright spot. So in this problem, it's at m equals 6. So really there are several missing bright spots, right? There's one at m equals 6, there's one at -6, there's 12. It looks like every 6 there's a missing bright spot. So those occur at the same position on the screen, right? It would have been a bright spot there had there not been diffraction. These occur at the same position on the screen. So let's try and write down a couple equations describing this spot. So we'll call this at theta missing. Okay, so really this is the first spot where it's missing. Okay, so let's try and figure out an equation right here. So the first missing bright spot well, we have d sine theta missing. This was m lambda, and this was m equals 6. So I'm going to go ahead and replace that m. So this is for our problem, original problem. Because I'm going to go ahead and plug in the actual value of m equals 6 right here. So the first missing bright spot has m equals 6. But we also have a sine theta for that same value of theta is equal to p equals 1. So remember, this is p lambda in general. So if p is a non-zero integer, you get a dark spot because of the diffraction effect. So I'm going to go ahead and plug in p equals 1, or maybe like that. Now if I take the ratio of these two formula, I'm going to take the first equation divided by the second equation. It looks like d over a is equal to 6. 6 lambda over lambda, which is equal to lambda. So we can see by looking at where by looking at the m value for the missing bright spot, we can see a relationship between the slit width and the slit separation. So it looks like d equals 6a for that picture. So that means the slit width is 6 times bigger than the slit separation is 6 times bigger than the slit width. So that tells us this right here. So d equals 6a. So 6 times 40 micrometers, looks like that's 240 micrometers. So it looks like our answer is 240 micrometers for the slit separation. Okay, so if we were to look at the slits, so they're separated by some amount, d, and they have some slit width, a. And it looks like for that particular picture, d equals 6a. So if you take the slit width and you multiply by 6, that's the center to center slit separation. So you could tune these two values and get different, and control how quickly the interference effect is going to die down, and then it kind of comes back. But really, this is a lot darker than the central one because of this overall diffraction effect. Okay, so the main things so the functional form here isn't quite so important. So you don't have to know that function, but you do have to know roughly what this function looks like for intensity versus y for diffraction as opposed to interference. And you do have to know about these missing bright spots. And so if you're told some information about, or if you're given a picture, you can figure out where these missing bright spots are and relate the slit width and the slit separation from that info. Okay.